Student, this is chapter 3, Mechanical Property of the Materials. Mechanical property of the materials is a very important measurement that we should understand for manufacturing process. In this chapter, we'll cover several different mechanical properties. There are stress-to-strain relationships, hardness, effect of temperature on properties, fluid properties, viscoelastic behavior of polymers. Those are very important, like a background knowledge for the materials. Mechanical properties determine the materials' behaviors when subject to mechanical stresses. So the property include elastic modulus, ductility, hardness, and various measure of strength. So here's some dilemmas. For designer, usually they would prefer the mechanical properties such as a very high strength. However, usually it's also made manufacturing more difficult. So understand those mechanical properties very important, not only in the design and also for the manufacturing. So we have to know, based on certain circumstance, how to manufacture the product based on the particular materials. 3.1 is a very important properties. It's about the stress and the strain relationship. So basically, what is the stress? It's try to put some force on that materials and to see what will happen. So there are three types of static stresses to which the material can be subject. One is tensile. Tensile basically you try to stretch the material and to see how happen on the materials. A second one is the compressive. It kind of squeeze. It's a total opposite to the tensile. It kind of squeeze the materials to see how happen on the materials. And third is the shear. Shear is causing the adjacent portion of the materials to slide against each other. So the force is not just the directional force is kind of sliding to the materials and to see how happen on the materials. So these three types of static stresses is very important: tensile, compressive, and shear. And here in this subsection, we will talk about a stress-strain curve. Here is a basic relationship that describes mechanical property of all types of these three types of stresses. So we'll continue talking about this. Section 3.1.1, tensile test. This is the tensile test is the most common test for studying the stress-strain relationship, especially for metal. So basically, in this test, a force is pull the materials. It pull. So the force is pulling. You kind of grab this material. It's one of the particular materials. You try to pull this force to create a tensile force. And of course, the material will elongate, and you get it longer. And also at the same time, this diameter of this bar, this test specimen is going to be smaller. So the tensile force applied on the right and the left and right, resulting in elongation of materials to do like this. So this is a very fundamental and very common test that we studied on the stress-strain relationship. So this is one of the tensile test specimens, and it's based on the American Society of Testing Materials (ASTM) that specifies preparation of testing. So you can see that's a gauge, that's marked here and here. So that's the original length, And that stress and the design is try to hold it on the machine. That particular machine is for the tensile test machine, and hold it very closely and then put a force on that. Then we can measure the how much of the millimeter, for example, the displacement have been elongate, and we can also measure the diameter on that. So this is a tensile test setup. So as you can see, those specimen is putting on that and you put a force, and this column is very strong. So you're trying to create huge amount of force on that. And so it's fixed basically, and there's moving from that, and try to create that the test, and the test can measure the elongation. So that is a sequences like this. In the very beginning, this this existing specimen, there's no load. Then we start to create a force, and of course, uniform elongation and area reduce. You see that it's smaller in this direction, and then when you reach to the maximum load, it reach the maximum load. If we continue to do that create a necking, and then necking we see the materials is going to have some fracture until it keep put a force, and of course this specimen is continue to elongate until that part is broken, and then we can come back to measure the final length. So that's the final length. So you can actually see this is the original specimen, and after we put a lot of force on that, and that elongates and make it much longer, like length. But of course the material is the same, the mass is basically the same, and since it's larger in terms of this length, then of course the diameter of this material is getting smaller if you compare this one. And also you see that some neck, and that is even smaller. Okay, and those neckings are happening because the materials have some when you force it's too much, and some of the weakening point will come out, and we can make it the material broken. It's broken there. Okay, we want to introduce several terms. First term is called engineering stress. Basically, it's defined as a force divided by the original area. So suppose there's a bar, right? Specimen, and you pull the force on that, and we also have an area. So we want to calculate engineering stress is calculated by that. Basically, it's a force divided by the area. So that is a very common way we do. And the engineering stress is just consider the original area of test specimen. So the original area of test specimen is can be measured, right? So that's what we call it, engineering stress. After introducing engineering stress, I want to introduce another term called engineering strain. If you consider stress is like a force, okay, then the strain is like how the material change. That's a particular way we want to measure that. So assume that, as what we say, the specimen, its original size is like this one, and you have a length. Okay, it's called L0, and after we apply the force on that, then he's going to be changing the size in terms of length. So this is going to be L. So we want to measure what's the percentage of a change compared to the original specimen. So that is how we calculate. So you can consider after we finish the testing the length minus L0 and divide by 0. So it's like a percentage, right? And this term we call the engineering strength. And we use this to define the trend, how the specimen change in terms of size. And this is a very typical engineering stress and strain plot. And it actually shows very interesting behaviors about materials. Let's take a look. You put a strain here, engineering strain, because we put an E, it's the engineering strain, and it's a stress. So as we know, this stress is F divided by A. And this is the elongation proportion, right? L minus L0 divided by L0, okay? Then we see the curve. If you, that's one of the particular materials, and if you apply the strength getting higher, that strength is also changed. In very beginning, you apply force, it is changed, but it is changed very constantly. With a very constant. This is a particular area we call it elastic region. That means if you apply the force, you change the size, but you release the force, then the size go back to original size. This is so that's why we call that elastic. Once again, you apply size, the force, you change the size, but you release, it come back. Until a certain point, that is a certain point called yield stress. After this certain point, they are not coming back. That way, once you release, it won't coming back. So that is what we call a change the stage to be the plastic region. In this plastic region, as you can see, when we apply the stress on that, it quickly increase the strength. That means that change in terms of size is getting larger. Do you see that? We maintain this constant, but after this certain point, it's getting larger in terms of size change. And you keep applying the force until it's called tensile stress. And also, what does that mean? That's a maximum loading. Then you see the stress coming by, the stress is getting larger and larger until the fracture. The fracture means that it's broken. Okay. So here is a very interesting and very important called stress and strain plot you have to understand, especially for elastic region and plastic region. Okay, the relationship between the stress and strain is linear, and it actually follows a certain rule. That the law is called S equal to E. E is called the modulus of elasticity. This is also known Young's modulus, very famous, called Young's modulus. Basically, it's a modulus of elasticity. So here is the stress. This one is the strain. Okay. But of course, this relationship only happens in elastic region, right? Because in elastic region is constant. And as what I just mentioned, materials return to its original length once the stress is removed. And E, this capital E, is a measure of inherent stiffness of the materials. Its value different for different materials. What I mean is, but still, this E is different for the for copper. This is different. All right. So this is a particular table 3.1 on the textbook, showing you the elastic modulus, or so-called Young modulus for selective materials. You can see for different materials, it comes with a different modulus. Okay, so basically, if you want to understand how the materials change their mechanical property in terms of the stress and strain, then you have to take a look at the table. look for the table and to see what's the number of that for the elastic, once again, elastic periods. Okay. And after the elastic periods, then we're going, the whole material change the relationship between the stress and the strain to be the plastic region. Okay, so a point in this linear relation finally reach when the material beyond to yield. Okay, this is called Y. So that's yield point can be identified by change the slope. And how to determine is by a certain way. You can take a look on that. So since it is a stress, so usually you can see this is straight line, and maybe it starts to change, but not much in the very beginning. So it causes a problem how to determine the exact point. Exact point is not easy because you probably cannot really see there's something changing here, right? So the way we did is the way to determine the yield point is, okay, we put a 0.2% offset from the very beginning point. You take the, because its strength is more like percentage, is right? Because E is equal to L minus L0 divided by L0. So it's a percentage, right? It's kind of offset the 0.2%. Obviously, it's 0.002. Then you take a look on this dash line and reach this particular point, and that we consider is the yield point. And this yield point has another names. Some people call it yield strength, yield stress, yield strength, and yield stress, and the elastic limit. But that means the same thing. That's that elastic behavior will be end at this point. After surpass this point, it's going to be the plastic region, the behavior change. Be careful on how to determine these yield points. You're supposed to see this in your homework. So the plastic region in the stress strain curve is, as Roger mentioned, is mark the beginning of a plastic deformation. And the stress and strain relationship is no longer guided by Hooker's law, no, because it's different. And as the law is increased beyond Y, elongation proceeds at a much faster, right, rate than before, because originally it's not that very fast, but after that it is going to be very fast. It causes slope of the curve and change it dramatically until you broke it. Okay. So here, we also need to introduce one of a term is called tensile strength. The elongation actually is accompanied with uniform reduction in cross-section area. It's consistent to maintain a constant violence because all violence didn't change. So, but cross-section will be changed. It will actually, the cross-section obviously changed, getting smaller, right? You can consider that. Okay. And finally, the applied low force, I've reached the maximum point. And the engineering stress at that point is called a tensile strength. What is tensile strength? Is the point equal to that, and that's the biggest one. It's the TS, a tensile strength. Also known as optimal tensile strength. And so that's how to measure that. The maximum of the force divided by the area A0. Okay, we will talk about this thing a bit later because people might argue that, well, at this moment, actually the diameter, the area already changed. Yeah, but anyway, in this definition for the engineering version, you still concerned by this way, A0. So if you're asking the engineering stress, then you still consider the A0. Okay. Here is the table showing the yield strength and the tensile strength of the selected materials. And by looking at the table, you can see the very different materials and metals. Both all of them are metals. They have a different yield strength, okay, and also the tensile strength, TS and Y, right? TS and Y. So it would be let us to understand what the materials is different. For example, some material you need to reach huge amount of stress that you would reach to the plastic. For example, like titanium alloy, it's very strong. Right? You can consider, right? It takes very strong force until you would change it to the plastic. But for some material, for example, copper alloy, no, I mean copper annealing. Yeah, it's only 70 MPa. You would reach to the plastic. Okay. And the largest is the tensile strength for the alumina. It's very small, as you can see, right? So alumina is very, usually people say, oh, it's relatively soft, right? That's what that means, right? Only 28 MPa, then it would reach to the plastic, and it can only reach to the 69, then you're going to be broken very quickly. So you compare this number with this number, so that we quickly understand titanium is kind of a very strong. Titanium alloy is a kind of very strong material compared to the aluminum, right? But aluminum alloy is metal material is getting better, right? It's aluminum annealing, aluminum, it's pure aluminum. But this is alloys, and that make it change. And as casting irons is a carbon, the carbon have alloys, and you make it stronger. So that's also mean that why the alloys sometimes have a very good mechanical property and make it stronger. Similar like that nickel, right? Similar like nickel and steel. Steel also considered the low C and the high carbon, low carbon, and alloy once again make it stronger. Okay, and stainless make it a little soft. Okay, you can see that. So this table is information where we can understand the materials of the different metal materials. Okay. In plastic region, as you see, there's size changes dramatically, right? You see the dramatic change. Okay, so that's what we need to calculate is the ductility measure. Basically, it's the elongation of EL. You use the particular size, right? As you see, there's a specimen until it actually broken, right? And the size larger, so it's a broken, that broken and fracture that the size is LF minus the original one and divided by the original length is a percentage, but elongation percentage. This one is the ductility. Okay. And the L is measured as the distance between the gauge mark after two pieces of pressure are put back together. So you have to put together because it's all broken, right? So that's how we calculate called EL. Okay. And also we see the area actually change, right? Because the original spaceman, you make it a little bit thick. And so we want to calculate this origin A0, that's origin final after the broken. So that we can calculate how much change in terms of area. So we can calculate that. Okay. It's called area deduction. So here is to show you a table 3.3 show the ductility as a percentage elongation for the selected materials. So it just to show you that for different materials, the elongation, how it will change. It will change the size. For as you see, wow, for aluminum anneals, it changed 40%. Wow, that's quite large, after the plastic. And for some copper alloys, it changes 60%. So you can see it must change very longer. So that's also mean that for those kind of materials that have a very nice plastic property, and can change. Okay, but for some ceramic, no way, no change. The porosity, no change. The thermoset probably is very small. But a thermoplastic polymer, well, it can be changed quite large. It's okay. So you can understand. And so, well, you can take a look. So we use this information. For example, cast iron is not really good, have a very good ductility. Right? It doesn't really percentage of elongation is just 0.6%. So you can check on that on the table.